So you should see the definitions of absolute extrema on your screen and local extrema. So we've covered local extrema so far in this course, finding local max and local mins. Now we're going to look at finding absolute extrema, absolute max, and absolute mins if they occur. So let's just go through these definitions really quick, and then we'll apply it by looking at graphs and looking at equations. So the definition says if C is a number in the domain of F, then we say f of C is an absolute maximum value of F if we plug in C in wherever we see an X in our function, and f of C is bigger than or equal to f of X for all X in the domain of F. Okay, so it's basically the largest Y value that we have on the whole domain. It's an absolute minimum, kind of the same sort of idea. So we say C is a number in the domain of F, so it has to be in our domain. Then f of C, the Y value, is an absolute minimum value of F if f of C, that Y value, is smaller than or equal to f of X for all of the X values in our domain. Okay, so let's look at that and compare the difference between that and what we just said. So a local extrema, so we say that C, we called it a critical point or critical value. If C is a number in the domain of F, then f of C is a local maximum value of the F if f of C is greater than f of X when X is near to C. So basically, we're saying, okay, if we can take a little interval around that value of C, and it's the biggest value around for those values of X, then that's going to be an absolute max, not absolute, local. And so likewise, we would say C is a number in the domain of F, then f of C is a local minimum value of F if f of C is less than f of X when X is near C. So we can create a small little interval, and it would have and that was the smallest value, Y value in there, then we'd say we had a local minimum when X was C. So looking at the example right here, here's a graph. And right now, if it asked us, find the absolute max and absolute mins of this graph. And right now, let's assume this picture is extending. So find your absolute extrema. So that's just plural, and it's just saying we're going to find your absolute maximum and absolute minimum value. And let's find your local extrema. So local max and local min. So looking at that, where is your absolute maximum occurring? And where is the absolute minimum occurring? Well, notice that if those values are extending on, so as X is going to negative infinity, our Y value, notice, is shooting downwards. It's always getting smaller and smaller and smaller, that Y value. And same idea here, as X is going to positive infinity, our Y value is shooting upwards, and there's no highest Y value that we would get. And so in this case, there's no absolute max or min. But we do have some local extrema. So notice, like right here, this is a high point if we had sandwiched it in between some interval. And so this would be the highest point of all those X value or Y values for all these X values in that interval. So we can see that we have a local max Remember the maximum value and the minimum value was the y value. So in here we have a local maximum of 0 at x equals 0. And then I noticed that we also have a minimum value. So notice right over here, this is the smallest point. And so the y value in this interval, we can make some interval around it. So we have a local min. So our y value is negative 0.203. And this is at x equals 0.571. Okay, so let's take that same picture and let's say that instead these were solid points here. So if we had solid points there, then that would change things. If that was a solid point here, this would have occur, our smallest y value is right here. And I could say, let's just estimate this. So that would be, let's say, negative 1.25. So we would have a absolute min. Let me just see. So this is 1, this is 1.5. Okay. So this is going to be negative 2.5. At x equals negative 1.25. And it has an absolute min of, sorry, not min. I was just thinking I just did min, max. And so that highest y value we're getting is 2 when x says, let's just say that that's 2. Our local max and local mins are occurring in the same place. So that's if those were solid points. So if we took the same picture and let's say that these were open circles instead of closed circles there, and it asked you to find the absolute extrema. In this case, there's actually no absolute extrema because you can give me some x value that's close to 2, for instance, right here, and say, okay, well, it doesn't exist in our domain. So if I gave you, let's say 1.9, let's say that was 1.9, that y value would give me, almost 1.9. But we could choose some x value that's even closer to 2. So let's say 1.91. That would give me even higher y value. So I could keep playing this game. I could choose 1.99. Well, you could choose something that was even closer to 2 that would even give me a higher y value. And so there's no single number that's going to give you the highest y value on that graph. And so if this is an open circle, they're not included in the domain, then in this case, there would be no absolute max and absolute min. So if these are open. Okay, so that comes to the point what I'm trying to make is this extreme value theorem. Also notice that, and well, let me just read the extreme value theorem, and then we'll talk about what I was just going to say. So the extreme value theorem says if f is continuous on a closed interval AB, then F attains both an absolute max and an absolute minimum value number on AB. So this theorem says if we have some continuous function, which we do up here, this is continuous on some interval, AB, and this is the main point I was getting at before, and it's a closed interval, so this would have to be closed. Then we're going to have an absolute max and an absolute min. So when we're going to find these absolute max and absolute mins, it's similar to what we were doing when we were finding our local max and local mins. We can use our first derivative, find when our derivative is equal to 0. So those would possibly give us a max and min values when our slope is 0, where it's undefined, but defined in our original. But we also want to test these values on an endpoint of our closed interval. Okay. So recall your critical numbers. Those are numbers where your function, they're in your domain and the derivative was equal to 0 or it didn't exist. So here's the steps to go through and find an absolute max and absolute min if they exist and the conditions hold for that extreme value theorem. So to find an absolute extrema of a continuous function on some closed interval, let's call it AB, we would say that to find all, first thing you're going to do is find all your critical points C of the function f of x on that open interval AB. So we're going to find our first derivative. We're going to set our first derivative equal to 0 and find if there's any value C where it's undefined. Then we're going to find the function values of f of C for each critical number C in step 1. So this is where we're actually plugging this back into our original function. We're not setting up those intervals where we were testing points into our derivatives to see where it's increasing or decreasing. We're plugging this back into our original function and getting back the y value. We also want to evaluate the function at those endpoints because we just saw on that graph that if we have closed endpoints, then we have a max and a min, and it could occur at those. That is, we want to find f of a and f of b. So you're going to look at all your y values you got back from your critical points for numbers and your endpoints, and the largest value found in step 2 or 3 will be your absolute maximum, and that smallest y value you get back will be your absolute minimum. So this is actually not as many steps and can be a little bit easier than what we were doing when we're trying to find local extrema. So let's look at some examples. But before I do that, let me see if there's any questions. Okay, so we're looking at an example where we're given that f of x is equal to x cubed minus 3x squared minus 24x plus 5. And it's asking us to find the absolute extrema if they exist, as well as all values of x where they occur for each function and specify domain. If you have one, then it says use a graphing calculator to verify your answer. We don't necessarily have a graphing calculator, but we do have Desmos, so we could verify this if you wanted to. So looking at this, conditions have to hold. So this has to be continuous on the interval it gives us from x equals -3 to +6. Well, this is a polynomial function, so this is continuous everywhere. And this is a closed interval because it has the bracket there. So it's saying we're including those values. Another way to write this right here is saying -3 is less than or equal to x, which is less than or equal to 6. Okay, so we need to find our critical values, and we can find that by setting the finding the derivative. So let's first find the derivative. So taking the derivative of x cubed, we get 3x squared minus the derivative of 3x squared, bringing down our power, 2 times 3, so 6x, minus derivative of 24x is 24, and the derivative of the constant 5 is 0. So this is defined everywhere, so we're just worried about when is this equal to 0, and those are going to give us our critical numbers. So I notice this is quadratic. I would first try, and I also noticed that they all have a greatest common factor of 3. So let's pull that out. So it could make factoring a little easier for us. We pull out a 3 from all 3 of those terms. We're left with x squared minus 2x minus 8. This is all equals 0. So let's see if we can factor this. There are 2 numbers that multiply to -8 and add to our middle coefficient -2, and that's -4 and +2. So this factors as x minus 4, x plus 2, and we still have that 3 in front. So now we can just set each factor equal to 0. Well, 3 equal to 0, no, that's never going to happen. But x minus 4 is equal to 0 when x is 4. And x plus 2 is equal to 0 when x is -2. So sometimes when we're finding these critical numbers, it's possible that they're actually not in our domain that we're looking at. So you always want to check that too. So x equals 4, does that fall between -3 and 6? Yeah. And x equals -2 also falls between -3 and 6. So we're okay. And now we want to test and plug them back into our original function. So we're going to plug our critical numbers in there, and we want to plug in our endpoints. I tend to just make a chart like I was going to plot points. So this is my x value I'm going to plug in, and my y value I get back plugging in x wherever I see an x, I get x cubed minus 3x squared. Let me just write it up here. Minus 24x plus 5. So I usually then just write my numbers from smallest to largest. And so my endpoint's gonna, on the left, is always gonna be the smallest. So I have x equals -3. I have an x equals -2. I have an x equals 4. And then I have my other end value in here, x equals 6. So we want to go in. This time, we need to figure out what the exact value is to see. So this is where technology could be very helpful. And let's just pull it up to save some time. Okay, so I pulled up Desmos, and once you get into the website, you're going to go, they've changed it a little bit. You're going to go to their math tools, and we're going to go to their scientific, calculator. We're going to define the function, and our function was f of x is equal to x cubed. And then we had minus 3x squared minus 24x plus 5. Oops. Let me go back up there, plus 5. We wanted to evaluate at our endpoints and our critical numbers. So -3 was one of our endpoints. So if we plug in -3 wherever we see an x, we get back 23. So f of -3 is 23. So let's just write that in. So now let's go back into Desmos and plug in -2. So it's doing the work for us. It's plugging in -2 wherever we see an x in our original function. Where did it go? So f of -2, we get back 33. F of 4, we get back -75. And then the other endpoints of our closed interval, we're plugging in 6. So f of 6, oops, that gives us back -31. Okay, so the value that is the smallest y value is when x is 4, we get back -75. So this is an absolute min. And then looking at the smallest value that we get back. So smallest y value we have is 23, and that occurs, oops, that occurs when x is -3. So this is going to be our absolute. What did I just do? What am I thinking? That is not our absolute max, is it? The largest y value that we have is 33, and that occurs when x is -2. So absolute max is 33 at x equals -2, at x equals 4. So not too bad. So pretty similar to what we were doing before again. Finding our critical numbers. We're doing a little differently to figure out which one is the absolute max and absolute min by plugging it back into the original, not seeing where it was increasing or decreasing. Okay, so our next example, again, we're finding absolute max, absolute mins on a closed interval. This is the closed interval from x equals 4 to x equals 6. And our function f of x is a quotient, and that's 8 plus x in the numerator, all over the denominator is the quantity 8 minus x. So first of all, we have to make sure that the mean value theorem would work, that there is for sure an absolute max and an absolute min on here. This is a rational function, so you have to worry about your domain. And in here, we have to worry about values which set our denominator equal to 0 because it's undefined there. And so I noticed that because of that, 8 minus x cannot equal 0. So if I solve for x here, x cannot be 8. Well, I'm okay because x equals 8 is not in this interval. And so the only place where this function is not continuous is at x equals 8. So on that interval 4 to 6, this is a continuous function. So we know that this is a continuous function. And so if it's a continuous function on a closed interval, then by the mean value theorem, an absolute max and absolute min have to occur, and it could occur on our endpoint. So we're going to look at when our derivative is equal to 0. And so taking the derivative, we need our quotient rule. And so using the quotient rule takes the derivative of our numerator, so derivative of 8 plus x, that's just 1, times our denominator, 8 minus x. minus our numerator. So put parentheses around that whole numerator, 8 plus x, times the derivative of the denominator. So derivative of 8 minus x is -1. And we're putting this all over the denominator quantity squared. So 8 minus x quantity squared. So let's simplify our numerator by distributing and then combining like terms. Well, I don't need that parentheses around that 8 minus x. And here, notice that this is like a -1 times a -1. So that's actually like a plus. And so really I can just drop my parentheses. This is 8 plus x all over 8 minus x quantity squared. So combining like terms, 8 plus 8, that gives me 16. Negative x plus x cancels out all over 8 minus x quantity squared. So I need to find when my derivative is equal to 0 and where it's undefined, but defined in my original. So, or in my interval too. So this is 16 all over 8 minus x quantity squared equals 0. So we kind of talked about, and I'll keep saying it every time we have a rational function or we're trying to solve for 0. We talked about we're really only worried about our numerator equal to 0 because we can clear our fraction by multiplying both sides by our denominator. And that would give me 16 is equal to, well, anything times 0 is 0. So whenever we're multiplying by that denominator to clear our fraction, it's always going to be our numerator equal to 0. Well, 16 can't equal 0. And so there's no number that sets our derivative equal to 0. So there's no solution. And then the only place where it's undefined is at 8. And at 8, that's not even in this interval. And it wouldn't have held if it was. So all we have to test are our n values. So we have to look at what's happening when x is 4 and what's happening when x is 6. And we're plugging it back into our original function of 8 plus x all over 8 minus x. So plugging in 4 into that numerator, I get 8 plus 4, that's 12, all over 8 minus 4, which is 4. So 12 divided by 4 is 3. So do the same idea. Now we're going to go back in and we're going to plug in 6, wherever you see an x in this function. So we get 8 plus 6, that's 14, all over 8 minus 6, which is 2. So 14 divided by 2 is 7. So the smallest y value is where our absolute min occurs. So we have an absolute min of 3 at x equals 4. And we have an absolute max of 7 at x equals 6. Okay, so same type of an example where we're finding absolute max and absolute min if they occur. This time we have a closed interval from -5 to +8. And f of x is equal to the quantity x squared minus 16. That quantity is raised to the 2/3 power. So we need to make sure that this is a continuous function. This would be continuous. I would just have to make sure that all values of x between -5 and 8 fall in the domain of this f of x. Let me just rewrite f of x a little bit differently, just to kind of show. but this 2/3 power we can rewrite as a radical, so that the denominator is what root we're taking. So we're taking really the cubed root of the quantity x squared minus 16 quantity squared. And so since this is a cubed root, I don't have to worry about that I can't have a negative underneath the radical. If this had been a square root, then I need to start being concerned. But because this is a cubed root, all values of x are in my domain. I can plug any number in there for x and get back a real number. And so I'm okay. And I know that this is a continuous function. F of x is continuous. -5 to 8 is actually continuous everywhere. And so the mean value theorem holds. And we're going to call it MVT, mean value theorem. And so the mean value theorem says, okay, well then absolute max or absolute min would have to happen either at a critical number, the value what sets our derivative equal to 0 or undefined, or at one of our n values of our interval that we're looking at. So we want to take the derivative of this. And I notice when we're taking the derivative, we're going to have to use our chain rule. So our outer function is this parentheses to the 2/3. So if we take the derivative of the outer function, so 2/3 of the inner, it stays the same, x squared minus 16, subtract 1 from 2/3, so 2/3 minus 3/3, that gives me a -1/3, times the derivative of the inner. So times derivative of x squared is 2x, and the derivative of minus 16 is 0. So if I kind of clean this up a little, I get f prime of x is equal to, well, I have this 2x times this 2, so I can think of this all over 1 if you want. And that is 4x all over this 3. And then I'm going to bring down this -1/3 power to make it positive. So this would be x squared minus 16 to the 1/3 power. Okay, so I need to look at where is this equal to 0 and where is it undefined. So f prime of x equals 0. Well, if we multiply both sides by that denominator, we're just setting our numerator equal to 0. And so we get when is for x equal to 0. And that's when x is 0. So one of our critical numbers is 0. We also need to look at when is f prime of x undefined. Well, we now have variables in the denominator, and so we cannot have the denominator equal to 0. So we can't have 3 times x squared. Let's just look at when this equals 0 to the 1/3 power equals 0. So let's divide both sides by 3, or we can just think of it, set each piece equal to 0. So 3 equals 0, it doesn't. And x squared minus 16 to the 1/3 equals 0. So remember, if you have some radical equal to 0, which this is really the cubed root, we can clear the fraction by multiplying both sides or raising both sides to the 3rd power. So I could raise this side to the 3rd power. I'd have to raise this side to the 3rd power. So that would be saying x squared minus 16 is equal to 0 cubed, which is 0. Call power to power rules of exponents as multiplication. So 3 times 1/3 is 1. So I can use the square root property here, or I can just factor this, x minus 4x plus 4. equals 0. So x minus 4 is 0 and x is 4. And x plus 4 is 0 and x is negative 4. So my critical numbers are negative 4, 0, and 4. And our endpoints was negative 5 and 8. So we're going to need to go in here, plug these values into our original function. So let's go from smallest to largest. So left endpoint is negative 5. Then we have a negative 4, 0, 4, and then we have 8. Plugging it back into the original function, which was, and to, I guess it doesn't matter. I was going to say, to me, it might be easier just to do it this way, but we can also go and plug this into decimals if we want. X squared minus 16 raised to the 2/3. So if we plug in, if we look at f of negative 5, that would give me negative 5 quantity squared is 25. 25 minus 16 is 9. So this is really be 9 raised to the 2/3 power. So 9, if you raise that to the 2/3 power, make sure that you put parentheses around the 2 divided by 3. And so that's going to give us approximately 4.3. So we want to do the same thing. We want to go in here. Now we want to plug in negative 4 wherever we see an x. So negative 4 quantity squared is 16. 16 minus 16 is 0. 0 raised to the 2/3 power is 0. Plug in 0 wherever you see an x. So 0 squared is 0 minus 16. So this is going to be negative 16 raised to the 2/3 power. So if we do that, we get, oops, says error. Well, this is, right, this is the cubed root negative 16 squared. So I'm not sure why it's telling me I have an error. Just pause for a sec. Okay, so the cubed root of negative 16 quantity squared is 6.3. If we plug in 4, wherever we see an x, that gives us 4 squared is 16 minus 16. That's 0. 0 to the 2/3 is also 0. And then f of 8. So 8 squared is 64. 64 minus that 16. So that would be 48, all raised to the 2/3 power. So raising that to the 2/3 power, we get that that is approximately 13.2. So we're looking for the biggest y value. So from 4.30, 6.30, 13.2. So 13.2. So we have an absolute max of 13.2 when x is 8. And then looking at our smallest y value. So we have 4.3, 0, 6.3, 0, and it can't be the max, 13.2. So 0 is the smallest number in here. And so notice that it occurs twice, and that's okay. And so at 0, that's our absolute min. And it occurs 2 different places. When x equals -4 and x equals 4.